So to give you a little bit of background on Hui and what he's going to be presenting. About 2.5 years ago at Utah, we started a Center for Synthetic Organic Electrochemistry. My background is in electrochemistry and using proteins, using enzymes for electrochemistry, but has historically been for sensors and energy applications. With this new center, I really wanted to see if we could sort of combine biocatalysis and electrochemistry for electrosynthesis. We applied for a position. He actually has his PhD in biochemical engineering from ZJU in China, then went on and was a research associate in the Institute of Bioenergy and Bioprocess Technology at the Chinese Academy of Science, followed up by a first postdoc in biological systems engineering with Percival Zhang at Virginia Tech. Then a short postdoc at University of Minnesota. All of these were, kind of focused on enzyme engineering for a variety of different applications, including at Virginia Tech, some electrochemistry applications. So he was really looking to get more chemistry experience. And I was looking to basically hire my first enzyme engineer. And so it was a very good fit. And to all the faculty out there, we are only as good as the students and postdocs that we hire. So I was very happy to have him join us about 2 years ago. Hui?
Okay, thanks, Shelley, for the very kind introduction. Today, it's my great pleasure to talk about the recent progress in material group, the application of enzymatic electrosynthesis for the production of chiral chemicals. So for the enzymatic electrosynthesis is to use enzyme as catalyst, especially oxidoreductase, to catalyze the organic reaction in electrochemical system. So the enzymatic electrosynthesis ES has the advantage of both electrosynthesis and enzymatic synthesis. For the ES, the electron transfer is critical. So currently we can use both directed electron transfer, DET, and mediated electron transfer, MET, to realize the electron transfer. Compared with DET, MET has much higher efficiency and is more suitable to be used for organic synthesis. And we can use free electron mediators to shuttle electron between electrode and enzyme. We can also use the redox polymer to immobilize the enzyme on the surface of electrode. The redox pendant of the polymer can act as the electromediator and shuttle electrons between electrode and the enzyme. So around the ES, our group carried out 2 projects: the upgraded nitrogen fixation from nitrogen gas to chiral amine, and the biphasic bioelectrocatalytic synthesis of chiral-beta hydroxynitrile. Firstly, I'm going to talk about the upgraded bioelectrocatalytic nitrogen fixation system. As well as we know, the Haber-Bosch process is the industrial process to produce ammonia. So the Haber-Bosch process has played important role in promoting the development of human society. But the disadvantage of Haber-Bosch process is also very obvious. It requires the high temperature, high pressure, and also it generates a large amount of CO2 emission. So in recent years, our group developed normal bioelectrochemical Haber-Bosch process based on the utilization of a nitrogenase. So the nitrogenase utilizes the electron from the oxidation of hydrogen catalyzed by hydrogenase to perform the nitrogen gas reduction and ammonia production at the mild conditions. But there is a problem. No matter the Haber-Bosch process or the bioelectrochemical process, the end product of nitrogen fixation is ammonia. Ammonia is a biochemical with low added value. So here, our first question is, can we find a new way to make the end product of nitrogen fixation surpass ammonia and achieve to some fine chemicals with high added value, for example, the chiral amine? In nature, only a few of enzymes can use ammonium as a substrate directly. So amino acid dehydrogenase is one of them. So this enzyme can use ammonia and to replace the carbonyl group of keto acid and to produce corresponding amino acid with consumption of reduced cofactor, for example, NADH. So in the presence of omega transaminase, the amino group of the generated amino acid can be further transferred to a keto substrate and finally to produce chiramine. So our second question is, can we combine nitrogenase, amino acid dehydrogenase, and omega transaminase to form a new conversion cascade and to realize the conversion from nitrogen gas to chiramine? Just as I mentioned, the reductive amination reaction required to consume a reduced cofactor. So the regeneration cofactor, the regeneration of cofactor is critical. So for the traditional enzymatic cofactor regeneration, the extra sacrificial substrate and regeneration enzyme need to be added into the reaction system. With the consumption of sacrificial substrate, the reduced cofactor can be regenerated. So for the electrochemical method, the cathode can be used as electrodonor directly and to realize the regeneration of reduced cofactor or some other reduced electromediator. So compared with enzymatic method, maybe the electrochemical method is a better option. Here our third question is, can we use electrochemical method to realize the regeneration of a cofactor and further drive the conversion cascade composed by nitrogenase, amino acids, dehydrogenase, and omega transaminase, and finally to realize the conversion from nitrogen gas to chiramine. So based on the mentioned considerations, we designed and constructed a new upgraded nitrogen fixation system. So in this system, the cathode supplies electrons to realize the generation of reduced methylation. The nitrogenase utilize reduced methylation to realize the reduction of nitrogen gas and the production of ammonia. And at the same time, the diaphoresis use the reduced methylation to realize the regeneration of ADH. And then the L-alanine dehydrogenase consume the generated ammonia and the NADH to catalyze the reductive amination of pyruvate and the generation of alanine. So finally, omega transaminase use alanine as amino group donor and transfer the amino group to the keto substrate for phenol 2-butanol, and finally to produce our target chiramine, the R1 methyl phenylpropylamine. So after construction and optimizing the reaction system, we use a parametric IT analysis to trace the reaction process. So the entire reaction process was partitioned into 3 stages by 2 different injections. For the first injection, the components of NADH regeneration and the reductive amination was injected into the reaction system. So for the reaction with and without nitrogenase, both of them have the obvious current response. That is because the reduction of NAD plus consume the reduced methylation and further facilitate the electron transfer between the cathode and the NAD plus. But for the reaction with nitrogenase, the current density decreases slower than that of reaction without nitrogenase. That is because the generated NADH and ammonia was utilized by alanine dehydrogenase to perform the reductive amination of pyruvate and the generation of alanine. So this reaction also consumed the electrons from the cathode. So for the second reaction, the keto substrate was injected into the reaction system. Only the reaction with nitrogenase has a current response. That is because the production of chiramine also consume the generated alanine. So the regeneration of alanine further consume the electrons from the cathode and cause the current response. So after the reaction is over, so we use the GC-mass to detect the generation of chiramine. So the results show that in the reaction with nitrogenase, there is a new peak. So this peak is the peak of chiramine. So after that, we also measure the concentration of chiramine following time course. So after 10 hours of reaction, the highest concentration of chiramine is about 0.55 millimolar, and the highest Faraday efficiency is around 30%. So then we also studied the substrate scope. So here we use a keto substrate with different structures. So and then we use a upgraded nitrogen fixation system to convert this keto substrate to corresponding chiramine. So just as shown in this table, so 6 of them can be converted to corresponding chiramine, and the optical purity of the product is pretty high. So all the EP value is higher than 99%. Besides chiramine, we also use this system to produce chiral amino acid. So briefly, the cathode realized the regeneration of reduced mesylation, and the reduced mesylation support the reaction of production of ammonia and regeneration of NADH. Here we use a new enzyme, leucine dehydrogenase. This enzyme can use the generated ammonia and NADH to catalyze the reductive amination of 2-ketohexanoic acid and the generation of leucine. So be similar to the previous case, we also use apparametric IT analysis to trace the reaction process. So after the components of cofactor regeneration was injected, so both the reaction with and without nitrogenase had obvious current response. But after the components about the production of amino acid was injected, so there only the reaction with nitrogenase has an obvious current response. And finally, the GC mass results show that the L-leucine was generated in the reaction with nitrogenase. So because the up-mentioned system still requires external energy input, so here we constructed a self-powered, upgraded bioelectrocatalytic nitrogen fixation system. So here, the conversion cascade was integrated into a hydrogen fuel cell system. The electrons from the oxidation of hydrogen catalyzed by hydrogenase can be used to drive the reaction cascade in cathodic chamber. So after we get the fuel cell system, we characterize the function parameters of the fuel cell. The maximum open circuit potential is around 242 milliwatt, and the maximum power density is 1.6 milliwatt per square centimeters. So when the fuel cell has the highest power density, the corresponding potential is 0.13 watt. So the working potential was set as 0.13 watt. So finally, we also studied the substrate scope. So here we choose 6 keto acid substrate with different structure, and use them in the system to produce different amino acid. So 5 of them can be converted into corresponding amino acid, and the EP value is also very high. All of them is higher than 95%. So summary for this project, the end product of this upgraded nitrogen fixation system successfully surpassed ammonia and reached high added chiramines or amino acids. The second point is the apparametric IT is a useful method to trace the reaction process. So in our research, the electrode was not only used as an electron donor, it can also be used as a biosensor to collect the useful electrochemical signal, for example, the current density, and then to monitor the reaction process. So this method, I think, is much more convenient than some other traditional method, for example, HPLC, GC, and the colorimetric method. Our second project is a biphasic system construction. So the target of this project is to produce chirobate hydroxynitrile. Here, there is 2 important research foundations. The first one is about 7 years ago, the researchers established a conversion cascade from alpha ketone to chirobate hydroxynitrile. This cascade was composed by alcohol dehydrogenase, ADHS, and halohydrogen dehydrogenase, HHDH. So the final product is ethanol for cyano 3-hydroxybutyrate. So this compound is important intermediate of atorvastatin. Another research foundation is Meteor Group in recent years developed several redox polymers. So among them, the CCPA polymer, its redox potential is lower than the reductive potential of NAD plus reduction catalyzed by diaphorase. So the CCPA polymer can be used to regenerate NADH. So in our research, in our project, we designed and constructed a bioelectrocatalytic system. In detail, the diaphorase was immobilized on the surface of cathode by CCPA polymer. The reductive pendant of the polymer can shuttle electrons from the cathode to diaphorase, and diaphorase can use the electron to realize the regeneration of NADH. And the ADHS can use NADH to realize the reduction of COBE to produce SCHBE, and then the HHDH can catalyze the conversion from SCHBE to final product RCHCN, the chirobate hydroxynitrile. So in this system, we also add organic phase. So organic phase can be used to increase the substrate loading, and then they can also realize the in situ extraction of our final product. So after we constructing the system, we measure the CHC concentration in both biphasic system and the single phase system following time course. So the results show that the reaction rate of a biphasic system is much higher than the reaction rate of a single phase system. So after 8 hours reaction, the concentration of CHCN in biphasic system is about 10 times higher than that in the single phase system. So here, our COBE concentration, substrate concentration is 30 millimolar, and after reaction, 90% of the substrate can be converted into the chirobate hydroxynitrile. So then we measure the final concentration of RCHCN. It's about 25 millimolar, and the EP value of the product is about 81%. And besides the CHCN, we also produce other two chirobate hydroxynitrile, and these two compounds have the aromatic ring structure. So the final concentration is lower than the final concentration of CHCN, but the EP value is higher. So the EP value of both of the two compounds is about 95%. So finally, we study the reason why the biphasic system has much better performance than the single phase system. So here, firstly, we measure the concentration of COBE in both of these two systems. The results show that in the single phase system, the COBE concentration decreased rapidly. That is because in the basic aqueous condition, the COBE has a spontaneous hydrolysis phenomenon. But in the biphasic system, the adding of organic phase decoupled the COBE from the basic aqueous condition and avoided the spontaneous hydrolysis. And then we also measure the stability of the electrode in both of these two reaction systems. For the single phase system, we need to add a DMSO as covalent to facilitate the dissolution of COBE, but this DMSO can dissolve the CCPA polymer, and then make the CCPA electrode lose the capability of a cofactor regeneration quickly. But in the organic phase, so we don't need to add a DMSO as a co-solvent. So the CCPA electrode is much more stable, and the lifetime of the electrode is extended compared with in the single phase system. So that's the reason why the biphasic system has much better performance than the single phase system. So the summary, the CCPA diaphorase bioelectrode catalyzes the effective regeneration of NADH, and the addition of organic phase inhibited the spontaneous hydrolysis of substrate and extended the lifetime of our CCPA bioelectrode. So finally, the conversion effect was significantly improved. So finally, I want to appreciate the help and support of my advisor, Professor Shelley Meteor, and also want to appreciate the help from my lovely lab mate and the entire Meteor group. So thank you for your attention. I'm very happy to take any questions if you have.
Hey, thank you so much, Chen. That was a great talk. It seems like we might be having some issues with the Q&A chat function. We're going to still keep trying to move forward with that. Anya and the panelists still are receiving the questions. So if you have them, I guess continue to please ask them there. Do we have? Okay, thank you.
Yeah, hopefully I managed to fix my audio issues and you guys can hear me. Yeah. So Hui, I have a question, really great talk. Can you comment a little bit about the role and the selection of the mediator? Do you need to tailor the mediator and its redox potential to your enzyme, or how do you select methyl viologen in one case or those cobalt-bending mediators in the other case?
Okay, so that's a good question because in our previous research, so yeah, in this research, we have already screening many different methods to realize nitrogen fixation. Because for the nitrogen fixation, the redox potential is very low. So only a few electron mediators can be used to support this reaction. So the methyl violation maybe is the best one. So that's the reason why in this project, so we have to use the methyl violation as electron mediator. Yes, because we need the redox potential is low enough to support the reaction of nitrogen reduction and ammonia production. And also because the redox potential of methyl violation is very low, so it's low enough to support the reaction of NADH regeneration. So maybe that's the reason why in this project we use methyl violator as the electron mediator to drive the reactions. So I think for some other research, for example, our research about redox polymers. So the principle is the redox potential of the electron mediator should be lower than the periodic reductive potential of the reaction. The lower, the better. So that's a principle to screening and to choose the electron mediator for the reactions.
I see. Thank you. And we have another question. Regarding the first half of the talk, were you able or have you considered to accommodate non-canonical amino acids as substrates? If yes, can they serve as substrates for the third stage too? And if the answer is yes, does it matter for the ultimate product, which is an amine, regardless of the position of the carboxyl group?
Sorry, so it's not very clear.
Sorry, so maybe I'll go stepwise. So for the first half of the talk, have you considered using non-canonical amino acids as substrates?
So yes, that may be a good question. Actually, so in the beginning of this project, we indeed consider use some unnatural amino acid as substrate and amino group donor. But in the practical research I found, it's a little difficult to find a suitable amino acid dehydrogenase to catalyze the regeneration and the reductive amination of corresponding keto acid. So that's the reason why we use alanine dehydrogenase to catalyze the reaction and use alanine as the amino group donor. So